Hey everybody, so the goal of this video is just to be able to go through all of the other questions that I haven't put in videos before to make sure that you've got the practice that you need, that you're getting comfortable with conservation of energy. Alright, so we're going to start with example number 5 in the notes packet here. So we have a block of mass 2.5 kilograms. It's sliding along a rough horizontal surface. The initial speed is 8.6 meters per second. It's brought to rest after a distance of 16 meters. We want to determine the magnitude of the frictional force. All right. Now, as I look at this, I see that I've got some mass, I've got speed, I've got a distance. Right. Now, since I know that I'm working with conservation of energy here, the mass and speed obviously make me think of kinetic energy, right? So I have some kinetic energy in the beginning. And then it talks about this external force of friction. So the external force of friction is going to do work. So this is not going to be a situation where the sum of the initial energies equals the sum of the final energies. That is not going to be true here. What we can do, though, is we can take the initial energy and then we can add in some work, right? Now, in this case, friction is working against the motion, so that would be negative work. But I'm going to go ahead and write that in. So I'm going to take my initial kinetic energy, and I'm going to add in the work that's being done, and then that should be equal to the final energy. Now, it does say that it's brought to rest, and so my final energy should be 0, right? It's not going up or down. It doesn't have any kinetic energy if it's at rest. There's no springs. So therefore, my final energy of the block Earth system, or just the block, should be 0. So now I can go ahead and I can put in my numbers. So for the kinetic energy, I can go 1/2 times the mass times the speed squared. And then I'm going to add in the work. And I know that work is force times distance. Now, I also know that work is the change in energy, but number one, I've already got the change of energy here. And number two, remember the question actually gave me distance, and it's asking for force. So it would be really nice to include those in my equation. So at this point, I can just go 1/2 times the mass, which is 2.5, and then times the speed, which was 8.6 meters per second squared, and then plus the force, that's what we're looking for, the frictional force, that's what's causing it to slow down, times the distance, which is 16, and then that should all equal 0. Now at this point I should be able to just kind of put that all into my calculator. If I go 0.5 times 2.5 and then times 8.6, remember to square it, okay, that'll give me 92.45. I'm going to subtract that to the other side, so I'm going to have F times 16 equals negative 92.45. And then when I divide that negative 92.45 by 16, I'm going to get a force of friction that is equal to negative, and it looks like they all have 2 sig figures, so I'm going to go negative 5.8 newtons. And it does make sense that it's negative because the force is opposite the direction of the motion. So there we go. We're able to connect some of these ideas: energy, work, forces, friction, right? Now, if I wanted, an AP question would likely say, okay, well, now find the coefficient of friction, right? And so you could do that. Now that you know the force of friction, you could connect that to the normal force, and you could find the coefficient of friction. All right? Awesome. So that is example number 5. Let's move on to the next one. We're also going to look at, we're going to look at concept number 3 on this page. So a hockey puck slides on an ice rink at 1 meter a second. So it's moving along its constant speed until it slides onto a carpet that somebody left on the ice. What an idiot. The puck comes to rest after moving 1 meter on the carpet. How far along the carpet would the puck go if the initial speed was 2 meters a second? All right. Well, hopefully you're recognizing that this 1 meter a second has something to do with the kinetic energy, right? So I have some kinetic energy when the speed is 1 meter per second. Now, what would happen to the kinetic energy if the speed is 2 meters per second? Well, hopefully you recognize that kinetic energy is 1/2 mv squared. And the velocity there is being squared. So if I double the velocity, I'm not going to double the energy. I'm actually going to quadruple, because that 2 is going to get squared here. And so I'm going to end up multiplying by 4. So I have 4 times as much kinetic energy. Now that's all good and nice, but the question is asking how far along the carpet. So now I need to connect my energy to a distance. Well, I know that the change in energy is going to be equal to the work, which of course the work is force times distance. Now the force here is friction, right? It's not enough, because I know a lot of you are saying, oh, so that's 4 times the energy, therefore it must be 4 times the distance. Hold your horses, child. Hold your horses. Because we also need to consider the force. Now, what is the force here? The force is the force of friction, right? That's the force with the carpet. Now, if my object was moving faster, would that affect friction? Now, hopefully you say, well, no, Mr. Bauer, it doesn't. And you would be right, because we know that friction depends on the coefficient and the normal force. Neither of those depend on speed. So the fact that it's going faster will not affect the friction, so the friction is going to stay the same. Now I can say, because the friction stays the same, if my energy quadruples, then my distance must also quadruple. So therefore, the answer will be 4 meters. Cool. Now we're ready to move on to concept test number 4. Okay? So concept test number 4 here, is the normal force doing work? Well, here the big idea is just this. Remember that the normal force, if a force is perpendicular to the motion, it doesn't do work. So that's really all we're looking at. If we look at the first drawing here, we see that the motion is down the hill and the normal force is up. So that would be perpendicular. So we would say, nope, the normal force is not doing work there. Same thing with the slide, right? The motion is down the slide. It is tangent to the slide. The normal force is perpendicular to the slide, so therefore, no, work is not done. How about in this one? With the forklift, the normal force is pushing up and the object is moving up. So now the normal force is in the direction of the motion, so we would say, actually, yes, it is. All right? And in the last one, we've got a person that is moving forward. The normal force that they're exerting on the bag is upward. Once again, this is perpendicular. And so we would say, nope, no work being done. Let's look at tension and gravity. Okay, we've talked about the pendulum before, how the tension is always perpendicular to, even they drew it in for us, the tension is perpendicular to the velocity, which is tangent to the circle. So because it's perpendicular, no, work is not being done. Now, in the case of gravity, if it is uniform circular motion, right, if it is going in a circle, then you will notice that, yes, it is always perpendicular. You have the centripetal force, the force of gravity going to the middle, and the speed is always tangent. And so in that case, no, work is not done. Now, we do have a slightly different situation in the case of a real orbit. Real orbits are actually not circular, they're slightly elliptical. Now, what that means is that in some places, the force is perpendicular to the motion, right? We can see that on the ends here. But there are other places, like right here, where the tangent to the motion, tangent to the ellipse, is not perpendicular to the force of gravity, which is straight towards the planet. So here, work is being done. Now you can see that the force is opposing the velocity a little bit, so the object would be slowing down as it goes out. As it comes back in, you can see that the force and the velocity have a parallel component in the same direction. So in this situation, we would say that it is gaining energy. So positive work is being done. So not only is work being done, but yes, sometimes the work is negative, and sometimes the work is positive. All right? So hopefully that helps to kind of make some connections and make some sense. We didn't get back to this in class, but I do want to make sure that we talk about it. We started the unit with this question, and we said, can we determine this? And the answer is, well, actually, yeah, we can, right? We start with the skier up at the top, where all they have is gravitational potential energy. So in the beginning, what we're going to do is we're going to say the energy initial is equal to the energy final, right? The only forces here are the normal force, which we just talked about, that's not going to do work because that's always perpendicular to the motion. And then we said, if you look back at example number 1, we said there's no air resistance, there's no friction, so therefore there's no outside forces doing work. All we have is the internal force. As long as we look at the skier Earth system, gravity is internal and we can consider the gravitational potential energy. So initially we'll have that gravitational potential energy, and then at the end all that gravitational potential energy will be gone and we will just have kinetic energy at the end. And so we can go mgh initial equals 1/2 mv squared final. Now, I know some of you are looking at it and saying, I'm at the bottom, I don't have the mass. It's okay. You don't need the mass because there's mass on both sides. And guess what? The mass, when I divide by mass, the masses, sorry, I should have used my red cancel pen. My masses cancel out. And so what I'm left with is G, which is 9.8. Notice I don't make it negative. It's just 9.8 times the height, which the height was 50 meters, is equal to 1/2 times the final velocity squared. And so now we can just go 9.8 times 50, which is 490. Then I'm going to divide by that 1/2 or multiply by 2, which is 980. So then I will have 980 is equal to final velocity squared. And then we will square root both sides. So square root of 980 is 31.3. I'm going to, looks like I do have 3 sig figs up there. I do have to be careful. The 9.8 is technically 2 sig figs, but that's all right. I'm going to go ahead and go with 31.3 meters per second. I have discovered the speed at the bottom of the ramp, even though the ramp is curved, right? That is the loveliness of conservation of energy. All right, let's go on to the next one. Okay, now on this one, we're going to be looking at concept test number 5, concept test number 6, and then 7 and 8 are in a separate video, so we're actually not going to go into those right now. All right, so concept test number 5. So let's go ahead and look at concept test number 5. So concept test number 5 says a marble rolls down a frictionless track and reaches speed v at the bottom. So I can already tell that this is a matter of gravitational potential energy that is turning into kinetic energy, right? I'm going to go ahead and cancel out the masses because that obviously doesn't matter. So I know then that GH turns into 1/2 v squared. All right. Now it says that I want it to reach a speed of 4v at the bottom. So how high do I need the track to be? All right. Now it's really, really tempting to just go straight for that 4, right? But if my velocity is 4 times greater, what is that going to do to my kinetic energy? Well, the velocity or the speed is being squared. So if the velocity is 4 times bigger and that's being squared, that means my kinetic energy is going to be 16 times greater than what it was before. Because the kinetic energy is 16 times greater than it was before, that means that my gravitational potential energy is going to have to be 16 times greater than it was before. Now, G is not changing, and because G is not changing, that means that the height must be 16 times greater than it was before. That then leads me to the answer of D. Be very careful. Don't just jump to 16 because it's a 1/2 mv squared, because if we were looking at elastic potential energy, we'd have to consider whether that one has a squared or not, right? So just be careful with these questions. Write it out. Take the time to think through it and consider it piece by piece. Consider every single variable, and you should be able to get these questions right. Okay? Let's take a minute and look at concept test number 6. Concept test number 6 says, at the bowling alley, a 4-kilogram ball is rolling back towards the ramp at a speed of 2.0 meters per second. The ramp leads the ball to a chute 0.5 meters above the ramp. will the ball make it up the ramp? Okay, well, there's really two ways to do this, right? You can either find out how much potential energy it's going to take to get it up to the top, right? To be able to get from the ground up to 0.5, I need a certain amount of gravitational potential energy. So if I find that, I can find out, do I have enough kinetic energy? The other option is find out how much kinetic energy you have and find out how high that will let you go. And if it lets you go up to 0.5 or more, then you're fine, right? So I'm going to go ahead and do it the second way, just because I think for a lot of you, you'd say, well, I've got the mass and I've got the speed, so why don't I just find that initial kinetic energy? So that's going to be 1/2 mv squared. So 1/2 times the mass, which is 4, times the speed, which was 2 squared. And so that's going to give me 8 joules of kinetic energy. Now the question is, if I have 8 joules of kinetic energy, how high is that going to allow me to go? So we will now look at the gravitational potential energy, the final, right? If I have 8 joules of energy, how high will I be able to go? So I'm going to go ahead and put the 8 joules in for UG. So I'll go 8 equals the mass, which is 4, times G, which is 9.8, and then times the final height. And I'm going to find out how high it can go if there's no negative work being done, right? If there's no friction, nothing working against it other than the force of gravity. Recognize that there is a normal force here, but the normal force is perpendicular, so it doesn't come into our energy considerations, okay? So I'm going to take the 8, and I'm going to divide by 4, and then I'm going to divide by 9.8, or you can multiply the 4 and 9.8, and then do 8 divided by that. And when I do that, I end up getting 0.204. So HF equals 0.204. I think it should be clear that that is not high enough, so the ball is going to roll up to 0.204, and then it's just going to roll right back down the ramp. Okay, so the answer is no, it will not, and here is my support, right? If you had used the UG, you would find that you need way more than 8 joules of kinetic energy, and so therefore, once again, the speed is not enough to accomplish what we want it to do. All right? Awesome. Awesome. Moving along. So on this page, we are going to do example number 8. Okay, we exert an upward force on a 0.15 kilogram baseball, releasing it with a speed of 20 meters per second. How much work do you do on the ball? Okay, we're going to assume that the change in UG, gravitational potential energy, is negligible. So remember, work is the change in energy. At the beginning, my initial energy, so this of course is final minus initial, right? That is work. Now, I know my initial energy is 0 because it does not have any kinetic energy. In the end, I'm releasing it with a speed of 20 meters per second. So therefore, I am going to have some final kinetic. I'm going to have some kinetic energy. Now, I'm going to look at the point right as the ball leaves my hand. Okay, I'm not going to look up at the top height because I don't know anything about that height. So I'm not going to worry about gravitational potential energy. I'm just going to look at the point. Here's my lovely hand. I'm going to look at the point right here where the ball has just left my hand with 20 meters per second. All right, so we'll go ahead and put that in, and we will go, the work then must be equal to the 1/2 mv squared, which is 1/2 times the 0.150 times the 20 squared. And if I put all that in my calculator, I get 1/2 times 0.15 times 20 squared, and I get 30 joules. Okay, so the work done is 30 joules. All right, now you'll notice that I didn't need to do the force times the distance this time. That's good. I don't know what the force is. I might be able to figure it out, right? I might be able to use some kinematics and figure out what the acceleration is and then get what the mass is. That's actually an interesting question, but for now, we don't have to do that, okay? The second part of the question then is how high will the ball go? Okay, well, we know that the ball now has 30 joules of energy. If it has 30 joules of energy, then as it goes up, it's going to get to its maximum point, and at its maximum point, it will just be gravitational potential energy. And so for part B here, I'm just saying, okay, well, when will the gravitational potential energy be equal to 30 joules, right? All of this energy is going to turn into gravitational potential. And so I'm going to go ahead and put my mgh in for that. The mass, of course, was 0.150. G is 9.8. And then I should be able to solve for the h that I get. And so I'll go 30. I'm going to divide by the 0.15. And then I'm going to divide by the 9.8. And I get a height of 20.4 meters. Now, the question does actually ask us if we can do it in two ways. The answer, of course, is yes, I can. And, of course, the other way is going to be using kinematics. So, for kinematics, we're going to list out our x naught, x, v naught, v, a, and t. My x naught is going to be 0. My x is going to be the maximum height. V naught is 20. Final velocity is when it gets up to the top and it has a speed of 0. The acceleration, of course, is negative 9.8. And I do not have time, and so I don't care about time. Therefore, I will use the equation that doesn't have time in it. And so I will go v squared equals v naught squared plus 2ax minus x naught. And I put all that in, and I should then get 0 equals 20 squared plus 2 times 9.8, sorry, negative 9.8, times x minus x naught, which is going to be h. Now I can just go 20 squared, and then I'm going to divide by the 2, and divide by the 9.8, and I should get the same thing as last time, right? So I should get h equals 20.4 meters. There you go. We worked out in two different ways. Nice job, us. Let's move on to the next one. All right, so here we are looking at examples 9 and 11. All right, so in the first question here, we're given a roller coaster. We've talked about how AP loves their roller coasters. We've got a frictionless roller coaster, barely makes it up to point B on its track. How fast does it travel at point A? And how fast does it travel at point C? All right. So it says it barely makes it up to point B. So I'm going to assume then at this point that my speed is 0. And therefore, if the speed is 0, the kinetic energy is also 0 at that point. Okay? From here, you can then work on the pieces individually. Now, one thing I do want to iterate is that when you choose a 0 point, you can choose a new 0 point every time you do the question. Okay, for example, let me show you. For I'm going to do part A first, right? How fast is it traveling at point A? So for point A, I'm going to define this as my height 0, right? And so when I do my change in height, the change in height is only going to be 10 meters. That makes sense because from A to B, it only goes up 10 meters, right? So at A, it has to have some kinetic energy. It's gravitational with the Earth's system, of course. The cart's gravitational potential energy is going to be 0 because it's at my height 0. And then as it goes up the roller coaster, it's going to get up to the top where we just said kinetic energy is 0. So therefore, it will only have gravitational potential energy at that point. Okay? Again, we're talking about the cart Earth system so that we are allowed to use gravity as an internal force. Okay? So we'll go 1/2 mv squared initial. That must be equal to the mgh final. Notice it doesn't give us the mass, but that's okay because the mass cancels out. And so then we'll be left with 1/2 v naught squared, which will be equal to g, which is 9.8, times the height, which we said that difference in height ends up being 10. And so now I can do 9.8 times 10, which is 98. I can divide by the 1/2. and then I can square root the 196, and I get 14. So therefore, the initial velocity must be 14 meters per second. So that is the initial velocity, which is also the velocity at A. All right. Now, at this point, I can either use A as my starting point and then end up at C, or, again, I can use B and then go down to C. I think the easier way to do this is probably start with B and go down to C. If you start with A, it's likely that at A you have both kinetic and gravitational potential energy. So instead, I'm going to go ahead and just start at B. So I have gravitational potential energy there. Okay? And then at C, all of that gravitational potential energy is going to turn into kinetic. So this time, I'm going to make this H equals 0. And that's okay, because this is completely independent from what I did before. So I'm going to start with the B. That's going to give me my initial gravitational potential energy. That's going to have to be equal to the kinetic energy at the end, or the kinetic energy at C. So I'll go mgh. The height this time is going to be 25, and that should equal to 1/2 mv squared. Once again, do not fret. The masses cancel out, and it becomes a fairly straightforward math problem. 9.8 times 25. Divide by that 1/2, and then, of course, square root your final answer, and I get 22 meters per second. All right, and remember, once you have this, you can actually just plug this into your calculator and do an insolve, right? You can tell your calculator to just solve that equation for you. You don't even have to do the algebra. You can, and some people will say, well, it's probably easier to just do the math, and if that's the case, go ahead and do it. But if you can save time by using the solver on your calculator, please do it, right? AP's okay with that. You're not getting points for algebra. You're getting points for answering the question. All right, let's move on to example number 11. All right, so example number 11. At the bowling alley, the ball feeder mechanism must exert a constant force to push a bowling ball up a 1 meter long ramp. So here's my 1 meter long ramp, and there's going to be some type of feeder here that's exerting a force on the ball up the ramp. The ramp has an angle of 30 degrees to the horizontal. If the ball starts at rest, so it's going to start with V equals 0 at the bottom of the ramp, how much force must be exerted on a 5 kilogram ball to get it to the top of the ramp? So the feeder is going to push the ball up the ramp. Remember, on the concept test before, we found out that the ball didn't have enough energy to make it up. So they said, okay, well, let's just create a feeder mechanism that's going to push the ball up the ramp instead. So how much work is it going to have to do? All right. Well, if you remember, work is the change in energy. Okay, so knowing how much energy we start with, how much we end with. So you can either look at this as work equals the change in energy, which is final energy minus initial energy. Or you can look at it the way that we did at the very beginning of this video. You can say, well, I start with this much energy. I need to add in some work, and that should give me my final energy, right? Now, final energy can be a combination of potentials and kinetic, right? But you may notice, it's about it, those are the same thing. Yes, they are the same thing. Yeah, you're correct. All right? If you don't see that, it's okay. You just add the E naught to the other side, and then you have essentially the same equation. All right? Now, initially, what kind of energy do I have? Well, I don't have any energy, right? So we don't have any energy, so that is going to be 0. Now, the next thing is, how much final energy do I have? Well, I definitely have some mgh, right? I definitely have some gravitational potential energy when I get up there. Do I have kinetic energy? We might, but the question is, how much do I need just to get it there? Not to get it there with any speed, but just for it to get up there. So I'm going to say that kinetic energy is a no. I don't have any speed. If I have speed, great. If there's extra work, wonderful. But the absolute minimum is to get it up there without any speed left. Okay? So that final energy is just going to be gravitational potential energy. Now work, of course, is force times distance. Okay? The final energy is going to be mgh. So now I can go through and start putting in numbers. The force is what I'm looking for. The distance is the distance up the ramp, so that's 1 meter. The mass was 5. The g is 9.8. And the height, oh, I don't know the height. I better figure that out. It's a good thing they gave me the angle, isn't it? So I got an angle. If the hypotenuse is 1, if I do my trig, I'm going to allow you to do the trig, but this should be 0.5. And so I'm going to go ahead and put in my height of 0.5 there. Now I should be able to just go 5 times 9.8 times 0.5. And that gives me 24.5. And then I divide by the 1. And I get that a force, a constant force of 24.5. I do notice that these all have 2 significant figures. And so I'm just going to go 24.5 is 25 newtons. And so that will be my final answer. All right, there you go. That's example number 11. Now, I think the only other question that we've not worked through yet out of the one required for you is concept test number 11 here. So we're going to do concept test number 11, and then we shall be done. So in concept test number 11, it says a 20 centimeter long spiral is attached to a wall. The spring stretches to a length of 22 centimeters when you pull on it with a force of 100 newtons. The same spring is now used in a tug-of-war. You and I each pull with the force of 100 newtons on the end. How long will the spring be while we are pulling? Now, this is actually not really an energy question. This is a force question. Now, a lot of people forget that when you attach it to the wall and you pull on it with 100 newtons of force, then the wall, so this is you, the wall must be pulling back with 100 newtons of force. If it wasn't, then the spring would leave the wall and accelerate in the direction of your force. And so therefore, this really is a Newton's law question, right, that they've disguised as a spring question, so don't be surprised if that happens. So the reality is, if you and I each pull with the force of 100 newtons, it's just the same as having the wall there, and so therefore the spring will be the same as it was before. All right? That is all of our questions. We've gotten through all of our concept tests and examples, everything we wanted to get through. So I hope that video was helpful, and we'll see you next time.